Good morning, good afternoon, good evening, class. This is Mr. Arocena, and on today's video, we're going to be talking about acid-base titrations and how to calculate acid-base titration problems. So this will be a lot of examples and a lot of calculations, but it won't be any different than the stoichiometry that you should have hopefully remembered from Chem 11. All right, so first things first, what is a titration? A titration is a process where a measured amount of solution is reacted with a known volume of another solution until an equivalence point is reached. Now, the equivalence point is basically, I have it here in my PowerPoint as where the moles of A, so this could be like your solution 1, moles of solution 1 match moles of solution 2. So solution 1, this was solution 2, where they make this ratio, and the ratio matches the mole ratio according to the reaction equation. Okay, for acids and bases, what this basically means is that at its heart, the amount of acid equals the amount of base in order to neutralize reaction, in order to fully neutralize. So for acid-base titrations, the equivalence point is when all of your acid has been neutralized by all of the base. So if you're adding base to an acid, the equivalence point occurs when there's no more acid and because you've added enough base, and the vice versa is true, is if you're titrating an acid into a base, then you've added enough acid to neutralize all of the base and nothing more. So that's what a titration is. Now the titration apparatus looks like this. Some of you might have used it in Chem 11 and maybe Science 10. You basically have the burette, which is a large glass tube, and it has measurements, very accurate measurements, and then you either have in the burette sodium hydroxide or an acid, usually a strong acid like hydrochloric acid, and then you slowly add to your unknown substance. So here we're adding base to an acid, but if you have an acid, then this would be or a base. The white tile is present simply because the white tile makes it easier to detect color changes, and we usually will add an indicator to give color added to give color. And the indicator will change color when the solution hits the equivalence point. We'll talk about indicators in more detail later in another video, but for now, this is what the basic titration apparatus it looks like. Now, titrations aren't limited to just acids and bases. You can do titrations with basically any solution-based chemistry, but the same sentiment applies in that you basically add a known amount. So this is known concentration in the burette, and you add it to some unknown concentration in the flask. And then your process is complete when the amount you've added fully reacts everything that's in the flask. Now, titration problems generally involve 5 things. So these are 5 parameters that all titration problems require in order for you to be able to solve them. The first is concentration of acid, and by extension, concentration of base. Following this, you'll need the volume of the acid, and you'll need the volume of the base. And then finally, you'll need the acid-base mole ratio you get from the neutralization reaction. Okay. More generally, this would be concentration of acid or solution 1 And this would be concentration of base or solution 2. So more generally, titration involves 2 solutions, but we're going to focus on acids and bases for now. With the volume and the concentration, that will allow you to calculate moles, because if you recall, molarity, so concentration, is moles per volume. So if you have the molarity and the volume, you can then calculate the moles as molarity times volume. And that's important because the reaction equation will give you the mole ratio, and this will allow you to sort of do the calculations necessary to find either moles of acid or moles of base, and then from there find concentration of acid or concentration of base, which is what most titration problems end up being. All right. So there you go. So that's the quick rundown of what a titration is, and kind of what we need to know, or at least what parameters are used in titration calculations. Reminder again that the molarity equation is moles per volume, and from this we can calculate the moles of the acid or the base that are present. And remember, in every titration we know the concentration of at least one of the substances, and that's the substance that's in the burette. Now the base acid ratio from the equation, once we figure out the moles of acid and base, we can use the base acid mole ratio to calculate the moles of whatever we need to find. Generally speaking, this will be the unknown substance, so whatever the unknown substance is, we can calculate the moles of the unknown substance, and then from the moles we can calculate the concentration based on the volume of the unknown substance we have. So let's go into some examples of how to calculate these things. So first example, we're going to do a neutralization of sulfuric acid using sodium hydroxide. So this is the neutralization reaction. Now some of you might be wondering, but wait, Mr. Arocena, doesn't the sulfuric acid only give away one hydrogen? And that would be correct, but I'm going to illustrate why we still require the 2 sodium hydroxides to fully neutralize the sulfuric acid in a moment. Okay, so in this particular example, the equivalence point occurs when we add 23.1 milliliters of this much sodium hydroxide is added to 25 milliliters of sulfuric acid of some concentration. So this is our unknown concentration. And then it asks us what's the concentration of H2SO4. All right, before we dive into the calculation portion, I'm going to explain a little bit why the H2SO4 still requires 2 NaOHs to neutralize. Because if you remember when we were talking about strong acids, H2SO4 had the interesting property where it would only give up 1 hydrogen when it was dissolving in water. So because our goal with the titration is to fully neutralize something, I'll just put the Na plus here, is to fully neutralize something. There we go. What ends up happening is that when sulfuric acid gives away the first hydrogen, you get this substance here. Now this substance has the ability to donate a hydrogen to any remaining water molecules. So this substance can then become I guess NaSO4 minus, and the water, because it's gaining a hydrogen from here, becomes H3O plus. So even though we really only need 1 sodium hydroxide to neutralize the 1 hydrogen that the H2SO4 gives, the remaining substance, the HSO4, still has the ability to react with water to produce hydronium. So the resulting solution is still going to be basic. So this hydronium here requires another sodium hydroxide to neutralize it so that it becomes sodium ions and water. That's why we require not just 1 sodium hydroxide, but 2 sodium hydroxides, okay, to fully neutralize, okay. All right, now that that's taken care of, let's jump into the math. So now that we've, I guess, solidified this 2-to-1 ratio of sodium hydroxide to sulfuric acid, what is the concentration? Well, first thing we're going to do is we're going to calculate the moles of sodium hydroxide. And that we can quite simply do because we have the volume and we have the concentration, so we can just multiply those together. I'm going to leave my milliliters in milliliters. You don't have to. You can convert it to liters if you want to. But if you want to save yourself a calculation, you can just leave it like this. This will give you an answer in millimoles. So 23.1 times 0.2055, we get 4.75, or I guess 4 significant figures, so 4.747 millimoles of NaOH. Now, at the equivalence point, so we'll call this at equivalence point, so not the same as equilibrium, at equivalence point, the 4.747 moles of NaOH has to match our 2 NaOH to 1 H2SO4 ratio. Millimoles of H2SO4. So this comes from our balanced neutralization reaction. So again, 1 to 2. And we can then set up this ratio to calculate how many millimoles of H2SO4. We can just again cross multiply and divide. So 4.747 times 1 divided by 2. So 2.374, I guess. 2.374. 2.37. Let's do a 35 millimoles of H2SO4. Now that we know how many millimoles of H2SO4 were present, we can then calculate the concentration of H2SO4. So the concentration of H2SO4 will be its millimoles, 2.3735. I'm keeping an extra significant figure because I have not finished my calculation yet. And now here's the part that some students will get confused, because the volume we use will be just this one, just 25 milliliters. So we're not going to use a combined volume, because the reason for that is that the concentration of H2SO4 comes from our 25 milliliter sample. If I added them together, that would give me the diluted solution of H2SO4 if I were to increase the volume. But because our volume of H2SO4 is started out at 25 milliliters, that's what we're going to use to calculate the concentration. So, carrying out this calculation, divide by 25, we get an answer about 0.0949 to 4 significance figures, 9494. There we go. So by doing this titration, we now know that that sample of acid has a concentration of about 0.09 moles per liter. Now, depending on the where we got this sample from, we can then report back and say, okay, your sample of water contains this much sulfuric acid, and then do with it what you will. Generally speaking, this type of calculation or this type of procedure would be useful in determining things like concentration of, acid in, say, like a wastewater sample. If you had a wastewater sample and you wanted to figure out how acidic it was, this would be one way you could do it. Anyways, so that's basically what a titration calculation ends up being. We just calculate moles of the known substance we're using, set up a mole ratio type equation similar to our stoichiometry from Chem 11, and then the end result is usually finding either a concentration or a mass of the unknown substance. All right, now for other polyprotic substances that aren't strong acids, sometimes they will undergo partial neutralization, so they will not go complete neutralization. This is very common for the polyprotic weak acids. The only sulfuric acid is the only polyprotic strong acid, and it kind of doesn't do this. But for polyprotic weak acids, they have the ability to give more than one hydrogen. So here's an example. This is a diphosphorus acid. So the possible reactions here are as follows. So we have our acid plus the water. So the first one is if the acid only gives up one hydrogen. Oh, whoops, why is that? That should be a P. 207. So if it gives up one hydrogen, it then becomes as follows. It could give up two hydrogens, create two hydroniums. It could give up four hydrogens. Oh, sorry, yeah, three hydrogens. You get the following. Or it could give up all of its hydrogens. Four hydrogens. 4 plus 4 hydroniums. These are your four possible reactions when working with this particular polyprotic weak acid. And all polyprotic weak acids are the same in that they have the ability to undergo one of these reactions. Now, given the nature of a weak acid, not all of these will be significant. One or two of them will be more significant than the others, and then that's where we'll get a partial neutralization, meaning that on average, the acid will give up a certain number of hydrogens, but not all of its hydrogens. How do we go about calculating what the average or what the more likely neutralization is going to be? Well, that's where we will do a titration. So here's an example. We'll take, in this particular titration, we end up using 25 milliliters of sodium hydroxide. And it reacts with the following amount of our tetraprotic weak acid. And we're asked how many hydrogens are removed on average. So what is the most likely reaction that occurs in this particular case? All right, so the first step is pretty much the same as the last one. We know how much sodium hydroxide we've used, and we know all the concentrations. So we can do the following. Moles of NaOH will be 25 milliliters times our concentration, and that'll give us the moles of NaOH. So that'll be 25 times 0.1255. So on average, based on our titration, we get this many millimoles of NaOH. Now, unlike the previous problem, we actually have enough information to calculate the moles of H4P2O7. So we can do this calculation as well, because we have the volume and we have its concentration. So we'll carry out that calculation. 38.74 times 0.0270, so we had 1.046. 1.046. I guess I could go, yeah, still be 46 regardless. Now, from here, I can write the following, because I know that my sodium hydroxide is going to react with my acid to produce water and some kind of, I'll leave the number blank for now. There we go. Some kind of hydrogen diphosphate compound with sodium stuck to it. But what we're really interested in is this ratio of sodium hydroxide to this ratio of H4P2O7. So it looks like if I put the numbers in, 3.1375, and this is 1.046. So it looks very close to a 3-to-1 ratio. And within reason, we can say it probably is a 3-to-1 ratio, because we can set up the ratio also like this. So that's approximately 3-to-1. Okay, and from that we can say, all right, since our data suggests a 3-to-1 ratio, then the most likely reaction, the H4P2O7, will most likely give up 3 hydrogens. Come this HP2O7 3 minus. There we go. So in this particular situation, on average, 3 hydrogens are removed. So this means that of the four possible reactions, okay, the donating of 3 hydrogens is the most common. It's most common. Okay, so that's not to say that the other donations don't occur. They just don't occur as often as the 3 donation one. There we go. So the titration data will allow us to determine sort of which is the most likely case to happen, and that'll allow us to do other calculations based on this new information. Now the third example deals with how we can use titration data to calculate the purity of the acid in question. Or I guess the purity of the salt, purity of the acid, yeah, purity of the acid. So here's an example where we dissolve some impure sodium bisulfate and we dilute it to 250 milliliters. And then we titrate this, or not the entire sample, just a 25 milliliter sample of this with 25 milliliters of 0.10 molar NaOH, and asks us what is the purity of the acid. So much like with the previous problems, our first step is to calculate how many moles of our sodium hydroxide did we end up using. So 25 milliliters times 0.10 moles gives us the following. I think it's 2.5 millimoles. So that's how many millimoles of NaOH we've used. Now, the reaction equation, the NaHSO4, this will dissolve into sodium ions, which don't react with water, and HSO4 minus, which will react with water to create SO4 minus and hydronium. So this is this thing we're going to try and neutralize. When we take that into account, we write our neutralization equation. Follows. The sodium hydroxide will neutralize the hydronium coming off of that. Give us HO. So, all right. So here we can safely say this is going to be a 1-to-1 ratio. So if I have 2.5 millimoles of NaOH, then I will have 2.5 millimoles of HSO4 minus. Okay. Now, based on this information and looking back at our dilution equation here, I guess our dilution equation would actually be this whole thing here. So not dilution equation, dissolving equation. Our dissolving equation is here. How does the dissolving of HSO4 minus coincide with the NaHSO4? Well, it appears to be another 1-to-1 ratio. So this tells me then that I've got 2.5 millimoles of NaHSO4. Now from there, this is actually 2.5 millimoles of NaHSO4 dissolved. Okay. Now, the 3.5 gram sample will figure out how many moles are in here gives how many moles. Well, here we just go back to how we calculate moles and based on mass. So if I remember correctly, going from mass to moles is a division by the molar mass, or in other ways, you multiply by 1 over the molar mass. So the molar mass of sodium bisulfate. Right, so looking up the molar mass of sodium bisulfate, it is 120.0603 grams per mole. Doing the calculation, 3.5 divided by 120.0603, we get a total mole amount of 0.029 moles. There's a 0.029 moles of NaHSO4 in 3.5 grams. All right. Now, going back to our 25 millimoles of NaHSO4 that dissolved, I should have said this earlier, that this is dissolved in 25 milliliters. So in 250 milliliters, we can expect 10 times that, so 25 millimoles dissolved, or 25 millimoles present. So in our 250 milliliter sample, we would expect 25 millimoles. Now, based on the 3.5 grams, we should have expected this many moles, and if I multiply this by 1,000 to get millimoles, this will be 29 millimoles. So this is what we should have expected, but this is actually what we got. So the percent purity is quite simply this. Percent purity would be the 25 millimoles we got divided by the 29 millimoles we were expecting. Let's multiply that by 100. Give us percent purity of 25 by 29 times 100, about 86%. So the sample of sodium bisulfate that we dissolved is only 86% pure. So titrations allow us to do quite a lot of things, and depending on the application, we'll be calculating, generally speaking, we calculate stuff regarding the unknown substance in the titration. Okay, so one last example. Here we have a 3.5 gram sample of some unknown monoprotic acid. We're diluting it to 250 milliliters. Then we titrate a 25 milliliter sample of this with the following amount and concentration of potassium hydroxide. And then we're asked, what is the molar mass of this particular acid? Now, a big assumption we're going to make here is that we're going to assume 100% pure. Otherwise, let's calculate this problem. It's a little bit more complicated. All right, so the process here is very similar to our previous example, where we calculate the moles of our known substance, KOH. So 17 milliliters times our concentration of 0.12 molar, and we'll get the following. So 17 times 0.12. We get 2.04 millimoles of KOH. Now the monoprotic part is really important, because then that allows us to say that the ratio of monoprotic means basically a 1-to-1 ratio of acid to base. So we can then say that if I have 2.04 millimoles of our base, the potassium hydroxide, then we have 2.04 millimoles of the acid in 25 milliliters. And then from there, because we diluted our sample to 250 milliliters originally, then we can say, therefore, we have 20.4 millimoles of acid in 250 milliliters. Right. Now from that, we can then take our sample in 3.5 grams. We have 20.4 millimoles, or in moles, this would be 0.04 moles. Then we can calculate the molar mass. Well, molar mass is simply grams per mole. So we can say, well, we have 3.5 grams of our acid, and there are 0.0204 moles. So this acid has a calculated molar mass of 3.5 divided by 0.0204, 171 point, if I round it to decimals, 157 grams per mole. Now, I should only have two significant figures, but in this context, it doesn't make sense to round off to two significant figures given the nature of what we are calculating. So we would look for, if I wanted to identify this acid, I would look for acids that had molar masses of around 171 and see which one is monoprotic, and then we could assume that's probably the most likely acid we're dealing with. There you go. So those are some example problems you can work with when you end up titrating things. Anyways, your assignment then will be to basically just do more of these calculations. The questions are as follows. If you guys have any issues, you know how to contact me.